We can hear you well.
I would like to begin by thanking the organizers for inviting me and expressing my regrets that due to events out of my control, I could not attend in person. Now, this is the outline of my talk, and so just to say that some of these ideas about the first half of the talk have been expressed in this paper in, you can see the reference here. If somebody likes to, I can send them the paper. My first slide is one which is almost a universal first slide for me now. This is a very interesting and important tale about Hoon's rule. Namely, Hoon's rule, which we all know and love, and which says that electrons in a suborbital will tend to align their spins, was interpreted in the 1930s that it was due to the repulsion in intra-orbital Coulomb repulsion inside the d orbital, for example. And this explanation stood for nearly 40 years until the quantum chemists discovered that it was completely wrong. The reason for the Hoon's rule for the alignment of the spins in the high spin state is not electron-electron repulsion, it is electron-nucleus attraction. What happens is that when the electrons are in the high spin state, the spatial part of the wave function is antisymmetric, and this has the weakest possible screening, which means that the nucleus attracts all the electrons strongly and the atom can contract. Essentially, the take-home message from this slide is that when the radius of the atom is a parameter which the atom itself can adjust, then the electron-nucleus attraction will be 10 times at least stronger effect than electron-electron repulsion, and it will be a mean field effect. Essentially, purely radial contraction gives you all you need. These are the papers. As you can see, they're quite recent given the age of the fields. Okay. So, what does it mean for cuprates? It means for cuprates that the DFT plus U is enough. You do not need DMFT or strong correlations to explain the arcs on the Fermi surface. This looks miraculous because in any one-body theory, the Fermi surface should close itself, okay? Not hang in midair like the arcs. But in fact, what is happening here is that there is actually a very large unit cell which includes the physical impurities which are not screened between the planes. This very large unit cell corresponds to some small zone which would be here and in which all the Fermi surfaces are as they should be. But when this small zone is unfolded into the large zone, which physically corresponds to averaging over the impurity sites, then the Fermi surface crossings end up hanging in midair. Here they are, you see, the red dots. And this is the calculation. You can see a preformed gap nicely dropping down to the Fermi surface. And here, the black dot is the first place where it bites. That is this slice 5, okay? So the point here, the point here is that this is a Fermi liquid, but not an adiabatic Fermi liquid, because its scales are set by the very large Coulomb scales of the out-of-plane unscreened interactions. So this Fermi liquid does not have to have the property of the standard Landau Fermi liquid that scattering feeds back into the effective mass. Now, interestingly enough, for the pnictides, the story is different. And the reason can be seen from the structure. You see, this is a cage of iron and arsenic atoms, and it turns out that the unit cell, the size of the unit cell, is adjusted by the arsenic ligands, but on the other hand, the metallic states, the Fermi surfaces are here, are due to direct overlap between the iron T2G orbitals, which means that the T2G orbitals are now as if in an atom of fixed size, and this means that the old Slater explanation of Hoon's rule is suddenly active, and there are elaborate magnetic correlations to show for it, and you cannot reproduce the experimental spectrum with LDA or DFT, if you like. DMFT is necessary for a correction. You can see the correction here, And it is not very big. It is between 100 and 200 millivolts, which is precisely according to the chemical narrative that these angular effects, so to say, intra-orbital repulsion effects, are typically 10 times smaller than the mean field Coulomb effects of the radial attraction. So this is a distinction between the cuprates and the pnictides. Interestingly enough, the cuprates, which have a curious Fermi surface, they can be explained in a one-body theory, whereas the pnictides, which have a quite ordinary-looking Fermi surface, need a many-body theory to explain the spectrum. Okay, next step. This is a brief summary. So we have two flavors of strong correlations, which I call radial and angular. Radial is now standard Hoon's rule. Large energy scale, the charge transfer between the oxygen and the copper adjusts the lattice spacing. So there is a size dependence, there is a charge transfer with ligands, but neighbors are not correlated. The copper is not correlated with the oxygen is uncorrelated, has no strong correlation. Well, in the pnictides, it's the opposite. You have a small energy scale, but angular correlations, and the neighboring T2G orbitals are strongly correlated. So you need the MFT. Okay, next step, we are getting closer to superconductivity now. Here, I have shown an experiment done in 2015 in Zagreb. I'm very proud to say this was the first time that the NQR signal was measured directly on the pure CT7 zinc substituted site. And what we found, much to our surprise, is that there is a symmetry breaking in that case. Namely, you see the oxygens here. This is a pyramid. This was YBCO. This is a pyramid of copper oxygens. And you see two oxygens are going down and one is staying in the plane. And this was shown in the experiment by forbidden 1/2, 5/2 transition in the NQR. This means that, in fact, we have elevated the oxygen, breaking of the oxygen degeneracy into a universally negative phenomenon for the superconductivity in the cuprates. In other words, what is the LTT tilt is doing only to LBCO, this zinc substitution is doing to all the cuprates. It breaks the oxygen degeneracy, and immediately the metal around this site becomes normal and it refuses to superconduct. So the oxygens, in other words, are very important to the mechanism. This is the lesson here. Next step. Now this slide, the first half of this slide, I've shown in Antalya 2 more years ago. This is the question whether superconductivity in cuprates could be purely 2D. There is a famous experiment of Božović, which I'm sure you are all aware, that they found a perfect Meissner screening in an atomically flat single layer. But there is an even older experiment which was done by Torque. And what I want to show you here is this black line, which would be followed by the dots if the material had a three-dimensional response. And the surprise here, the superconductivity were isotropic, I want to say. And the surprise here is, that is also YBCO, that as you go down in temperature, it becomes more two-dimensional. It departs from three-dimensional. So essentially, both experiments go in the same direction, that the superconductivity is intrinsically two-dimensional. And now, 2 years ago, I had some speculation here why that could be so, but now I know the answer. This is a paper we published just this summer. It turns out that the Hohenberg-Mermin-Wagner theorem is completely ineffective for two-dimensional superconductivity if the Fermi energy is much larger than Tc. In that case, the sample would need to be larger than the observable universe in order to have enough infrared fluctuations to destroy the order parameter. Now, I say 1 down, 2 to go, because still, as far as I know, BCS in the cuprates, where there is a pair size cutoff at lattice spacing, has not been explored. And BCS in real space, in the sense of non-overlapping pairs, but not BC, has also not been explored. So essentially, before we write off Cooper scattering as the essential instability in the cuprates, somebody should do a good job of these two lines. And I think the tale of Hoon's rule shows that sometimes just trying harder can lead to a huge payoff. So finally, before I'm done, let me introduce a new player with these same orbital ideas. The idea is to understand what the orbitals are doing. And we have found that in the cuprates, the oxygen orbitals are very important. Now, on the other hand, as I said, the pnictides are in a different regime. And so here the idea is to introduce a compound which is an interpolation between this and that. And here I have to really say that Neven Barišić has been a driving force behind this synthesis. This is the first time that anybody has obtained large single crystals of Murunskite that is ordinarily found in some microscopically small crystals in some Siberian massives. Anyway, the point of this compound is that it is an interpolation compound. As you see, instead of oxygen, it has sulfur, which is the next element down in the periodic system from oxygen. And on the other hand, you see structurally it is very similar to the pnictides, except that the metallic site is occupied by a mixture of iron and copper. So it's really an interpolation compound by the looks of it. And I'm glad to report that also electronically it seems to be an interpolation compound. This is the density of states here. It is a 0.8 electron volt gap insulator, okay, like the parent compound in the cuprates. But what is more than that is that the valence band is very cuprate-like. You see it has a lot of copper, that's green here, and a lot of sulfur, that's red here. On the other hand, the conduction band is very pnictide-like. It has a lot of iron and very little of the ligands. So we plan to play with it and see what comes out with this idea that this material could be used as a sort of analog calculator. Instead of having a big computer, have a little crystal, so to say. And as an analog calculator to probe it with various dopings and see where it goes with metallicity and hopefully superconductivity. So, to conclude, there are two flavors of strong correlations, radial and angular. DFT plus U, the very standard workhorse calculational method, can treat the radial correlations, and it explains the Fermi arcs as a simple kinematic one-body phenomenon of this projection of a small zone onto the large zone, which is observed spectroscopically. Superconductivity in 2D does not violate the Hohenberg-Mermin-Wagner theorem, essentially because the samples are smaller than the universe. And Fermi liquid and very local Cooper pairing, I would say, are still compatible with experiment. But the adiabatic Landau Fermi liquid with overlapping pairs is not compatible. And big takeaway, oxygen states matter. Now, finally, I would say modern functional materials are actually between physics and chemistry, and physicists who think that they can cut off the chemistry and just play with the equations, I think are doing so at their own peril. So learn what the orbitals are doing and think of Murunskite. And so I thank you very much for your attention.
Thank you very much. Thank you. What did you mean by talking about orbitals? Because one thing we heard today, actually implicitly in the first talk, is that since Phil Anderson has left this world, we have less of these kind of very high-level broad theorists who just put equations, and we are probably approaching more closer the truth, as you imply in your talk. Would you kindly comment on that? Because you seem to be saying that it's very subtle with oxygen.
Well, some people like to approach the problem from the side, so to say, of some very simple model. and others wait to develop the model until they understand all that is happening, or as much as they can of what is happening. And I belong to the second kind. That's all I can say.
Yeah, but we had the talk, so could you come in, please? Just a second, you'll get a microphone. Just a second.
Just what specific thing do you want me to comment on?
You will hear it now. You'll hear it, Katrin.
That's
Well, I had a bit of different question. This local Cooper pairing that you advocate, would you say that it could be generated at higher temperature or energy, or it's a zero temperature feature for you?
Okay, yes. Thank you for the question. The point is that you have these very, very large background Coulomb scales which determine the dispersion of this Fermi liquid. But then this Fermi liquid scatters strongly, I think, and at short range by something which is compatible with the big U usual story. Okay, so the point is that there is a large scattering scale which is still much smaller than the scale which determines the effective mass. So in other words, this large scattering does not feed back into the effective mass, and this is how the material avoids the catastrophe of the adiabatic Fermi liquid, which, as we all know, if it has too strong an interaction, then the effective mass diverges. This is not what is happening here, because some even bigger scale is determining the effective mass.
Okay, thank you very much for your comment.